Good afternoon, everybody. Our guest speaker today is Dr. Afşar SARANLI. He's a real expert on robotics. He's from the Department of Electrical and Electronics Engineering. Dr. SARANLI, could you please also introduce yourself in the beginning of your talk? The stage is yours. Thank you very much.
Welcome, everyone. So I don't consider myself an expert in this field because that's really a challenging field, and I really feel humbled about, maybe having some small things to contribute into this field. Essentially, what I'm going to try to talk about, and I kept my talk, let's say, in a way that's not going to bore you in this nice Matthew afternoon, spring afternoon, let's say. So what I'm going to try to talk about is essentially legged robotics. And the motivation behind legged robots, the motivation about having vision research related with legged robots, and some related stuff. These images are basically from our lab and some of our experiments. I want to start with having an outline of what I'm going to talk about. I will first talk about myself for a very short, brief period, just essentially giving you an idea about my background. Then I will talk about who we are, in the sense that as a research group, as a set of people working in this field. Then I will move on to talk about our general field of study. I will try to motivate you guys related with why to do robotics research, and legged robotics in particular. Then I will try to cover some research topics that we have been working on for the last pursue in the coming years. And please stop me and ask if you have any questions related with any part of it. Initially, I had planned this to be more of a discussion type lecture, but since I didn't have enough time to structure it that way, it ended up being a... But still, if you ask questions, we can spend time to discuss any particular part of this presentation. So I graduated from Electrical and Electronics Engineering in '93, and I went to England for my master's degree. It was related with... my master's topic was in telecommunications and signal processing, and it was more on the signal processing side. Basically, I worked in processing real-life signals, trying to detect certain type of system behavior. So my research was in that axis. Then I came back in 1994 to start my PhD studies here at the Electrical and Electronics Engineering Department. I was part of the control systems area, so my PhD was focused on control systems, but more on the signal processing side of things again. I basically worked in speech processing, trying to capture certain properties of speech, particularly related with who's speaking in a given speech pattern. So it was more of a pattern recognition type of work. When I finished my PhD in 2000, we wanted to have an industry experience, so we went to Canada for working in industry. So I was out of university for about 5 years. I was working in industrial automation, and particularly in the area of the inspection of liquid crystal panels. Like these LCD panels, during their manufacture, there can be many manufacturing defects, and these defects are usually detected by electro-optical systems, quite large because many panels are printed onto a single glass sheet. So you have huge systems which have certain type of scanners that scan the glass and try to detect manufacturing defects. I came back in 2005, and I'm kind of horrified to see that it's been around 10 years since I'm back. And I started in the electrical and electronics engineering department and started doing robotics research. My brother was also working in the area of robotics, so we basically started working in related areas that was both linked with image and signal processing, automation, as well as his area of legged robotics research. And here, I'm teaching control systems, I'm teaching robotics at a graduate level, and I'm also teaching the design courses of our department for the senior level students. Okay, so I also want to kind of have a short slide like this to essentially remind you that you are at a very privileged place, because our university, our campus, and our research environment is really something distinct, what you can find in Turkey. This is a very exciting place to be, both as a student and as an instructor. Okay, this is a place with international recognition. This is a place where there is huge amount of funding being drawn, both national and international funding. So there is a lot of possibilities to conduct excellent research. All we need is really students like yourselves that are motivated and that are prepared to do hard work and essentially exploit what is available in the campus. Okay. So who are we? Well, when I came back in 2005, I took over the department's robotics and autonomous systems laboratory. So I started working with my students in a fairly small laboratory inside the department. And we started, as you will see, we started having certain projects. So with some funding, we started to kind of accelerate the lab in a way that was conducting research in our field. We also recently, maybe 1.5, 2 years time, we are also trying to establish, in fact it is already established, but an interdisciplinary robotics laboratory. It's located in this colorful building in our campus, which is known as the Zimmer laboratory. It's a center. But its top floor is occupied by research groups, which are independent from the Zimmer Center. We have a unit there, and we try to collaborate between 3 departments, specifically mechanical engineering, electronics engineering, and computer engineering. My brother is teaching in the computer engineering department, and our project partner, Professor Yiğit Yazıcıoğlu, is in the mechanical engineering department. So we try to conduct interdisciplinary research pertaining to the robotics field. Okay, so now what I want to do is actually start to show you a number of videos that actually motivates us, and I think will motivate you in trying to understand why we should conduct legged robotics research. Okay. Now our field, our general field of study is known as dynamically dexterous legged locomotion. Okay. Now what we mean by dynamically dexterous is that we are not into designing legged robots that are kinematically stable. That means we do not do legged robotic research where robots are just moving one leg at a time and they are constantly stable on the remaining legs. Okay? The kind of robotics research that we conduct is really related with dynamic stability. Okay? The way that many mammals, as I'm going to show you, like human beings in running, okay? We basically balance ourselves constantly, and we have tremendous capability in terms of both maintaining our balance as well as being able to run, jump, perform many tasks that are quite difficult for today's computers and today's machines. Okay? So here we have the world's fastest athlete, as you might already know it from the press, right? basically he's running a 100-meter sprint. This is a video that is shot at a very high frame rate, so that you can see the individual control that he has over his body. Okay, you can see that there is a large amount of time he's in the air. Okay, so this is not like a locomotion where you put your foot on the ground and then balance yourself while you're moving your other leg to the new position. Okay, you might have seen Honda's very popular robot, which is quite impressive, but is unable to basically perform such a magnificent task. Okay. Now, is humans the only way animals, or because humans are also animals, right? But we know that humans are not the only ones having this excellent motion capability. Four-legged animals as well, okay? This is the fastest four-legged animal on the planet, okay? It's known as the cheetah. This is again a very fast frame rate video. In fact, you should be able to, let me enlarge this. There is the time indicator at the left, top left corner. You will see that we are still at half a second while this motion is happening, okay? And you can see that again, you know, the motion of the animal is so dynamic that it's barely touching the ground, okay? There is also the energy efficiency here, okay? We can see that the animal is expending energy, but most of the energy is really expend to doing the motion. There is very few amount of energy being lost in the process, okay? There is no energy lost compacting the ground, okay? And I also would like to note a couple of things that are also very relevant for us. One thing is how stable the animal's head is, okay? Now the animal is almost flying in the air, barely touching the ground, but the head, which is, as you know, is carrying most of our sensors, right? The head is carrying our vision sensors, the head is carrying our gyroscopic sensors, which are in our inner ear, right? Basically, our heads are so important that we have the mechanism to keep the head very stable while we are conducting all the motion that we have to, okay? Now, this video goes on, okay? There is also other parts where there is some experiment being conducted, okay? Some guy is pulling some kind of a target in front of the animal, okay? But there is so much to learn about how these animals are able to locomote and how they achieve their both their speed and their balance when they are executing these motions, okay? Now we might say, or we might ask, let's say, is this all about speed? I mean, these are, human running is quite fast. Obviously this is the fastest, or let's say for its size, it's maybe one of the fastest animals, okay? But it's not all about size, okay? It's about accessibility. It's about which parts of the planet you can access if you are able to build machines that are imitating, you know, legged animals. I will now show you another animal, which is quite different from what I've shown you, okay? Maybe you have seen this from National Geographic or similar TV shows, okay? Now these are mountain goats. As you might know, humans are quite good at climbing. You know, we have many mountaineers. We try to climb everything that we can, but humans are not that good in climbing when you compare them with mountain goats, okay? Mountain goats can go pretty much everywhere on the planet. If you think about the kind of systems that we can build today, like cars, you know, tanks, or, you know, some legged robots and so on, we are still quite far away from being able to reach, you know, many parts of the planet, okay? So potentially, there is a lot to be learned in terms of having legged robots that can reach the planet's surface to places where we can't reach right now by our conventional vehicles. Okay? I mean, if you're interested, these are all basically on the web. Okay? This is all YouTube. If you can just type the proper keywords, okay, there's a lot to actually learn from these animals. They can climb everywhere. I mean, the sheer cliffs of mountains. If there is a foothold that is as large as this animal's foot, it's going to be able to climb there. And at the same time, it's not climbing just in a way that humans are, you know, climbing with pulling themselves and so on. They are just jumping, you know, very happy, without any concern about, you know, the height or whether they might fall and so on. And they are, you know, so agile and so capable that probably, you know, from time to time some of them would be perishing, but, you know, still the capability is there. Now, after watching these, you know, one might wonder, you know, obviously these are animals and humans, you know, these are so much ahead of the current technology. We can't do this today, okay? But in fact, we are at a point right now where research is on the verge of making machines possible to imitate the behaviors that we can observe in the nature, okay? In fact, this research started very early, but it didn't catch up that fast, okay? Now, this video that I'm going to show you is from MIT's Leg Laboratory in the 1980s, okay? 1980s, as you know, is the emergence of home computers. You know, computers are quite rare. Home computers are quite weak, okay? But this guy was basically genuinely interested in legged robots, and actually has spent quite a bit of time in MIT building machines that were not just slow and cumbersome, but machines that are agile in the sense that by hopping, you know, dynamically balancing themselves. Basically, we will go a bit along this video to see the kind of machines that these guys have built in the early 80s. Okay. Now there are single-legged hoppers, there are multi-legged quadrupeds, you know, 4-leg, 2 legs. They have tried quite a bit of things. Okay. Unfortunately, the technology at the time required this thing to be really tethered in the sense that most of these things were pneumatic. They were using pressurized air in order to drive their actuators, so that, you know, there is always some kind of a connection to a power source where, you know, power is being delivered to this system, okay, in the form of compressed air, in the form of electrical energy, and so on. But still, you know, quite a bit have been achieved at quite an early time, okay. It's interesting why this didn't, you know, immediately catch on to build, you know, very powerful systems. But this guy was basically very determined. Actually, at some point he decided that he couldn't do this. He couldn't pursue this in the university. He basically founded a company called Photon Dynamics. Sorry, not Photon Dynamics, but Boston Dynamics. Okay, Photon Dynamics is the company I worked in. So similar name, hence the confusion. Okay. Now, this guy actually founded Boston Dynamics, and they struggled for a very long time. They built simulators. They built, you know, simulators to simulate military, let's say, military motions, you know, to test some suites and so on. So they were like, you know, selling auxiliary stuff in order to survive. But recently, the guy started attracting huge amount of funding and actually started creating very impressive devices. Okay. Now, I want to very briefly touch upon some of these systems. Some of them you probably have seen if you are really interested in this kind of work. Okay. Now, one of the first thing that, by the way, this company was part of the research that my brother was conducting at the time, about in the time 2001 and so. Okay. So, for example, this one is known as the big dog. Okay. This is one of the field robots that these guys have built. Okay, carrying a lot of equipment, being able to move in the field. What is lacking? Certainly the motion is there. Okay, this thing is able to balance itself through control algorithms and is able to carry loads, balance itself. Okay, but what is missing is the sensory capability. This thing is still being driven by a human operator through a remote control. Okay, and although I'm not opening up the voice, there is also a gasoline engine inside which is powering the hydraulic actuators that this thing is using. Okay, maybe you have seen this. This thing can even balance itself on ice. Okay, so you can see that it's slipping, but control algorithms are trying to balance by moving the legs in order to conserve essentially the balance of the robot dynamically. Okay, so this was quite early on, still very impressive. And the video is quite long, okay? It just, since this is kind of a pitch video, they are also showing this to military people that are funding the research. So they move it to mud, you know, all kinds of interesting places. It's a very impressive point of research. I mean, you have to respect the guy. I mean, he started doing this research in 1980s. Have done it relentlessly for the entire period, and right now in Boston Dynamics there is about 60 PhD engineers. Okay, so it's larger than our department in terms of qualified engineers that are doing research. Okay, maybe the good thing is that these guys publish nothing because they are very secretive. They are working for the military. They don't publish anything, so everything they can do is just, you know, contained within this company. And they are unique in the sense that there is no other company that is able to do this kind of research. Okay, there is only one company, so it's quite impressive. Now I'm going to show you a couple of more before I move on to what we can contribute to this kind of research. This is quite recent. Okay, this is again built for the military, able to operate entirely in its own power. So it has a gasoline generator. It can generate hydraulic power, so it can drive its actuators through hydraulic power. Okay, I'm going to fast forward a bit. This thing can run imitating gaits of four-legged animals. Some of these gaits you have seen from the cheetah. Okay, so this thing can run quite fast using a variety of gaits. Gait meaning leg patterns to touch the ground. You can see that it can. You can see that it can fail. Also, it can spend some time in the air, like the other animals can do. Okay. This is scary and impressive and exciting at the same time. We might see some of these in the military field quite in the near future. Okay. So unfortunately, Turkey is quite, let's say, not very excited in terms of, let's say, funding from companies goes. Our defense companies still are quite far away from these concepts. Okay, they still are borrowing yesterday's technology to build products. Okay, but the future's products are things like that. Okay. Now these are what is on the field. So what is in the lab is yet more impressive. Okay, this video is from the laboratory. Okay, this is a quadruped that is built for speed. Okay, so it tries to maintain control. You can see that there is a tether. Power is coming externally. There is also a safety net so that when it fails, you don't lose the entire thing. Okay, so this thing is running on a conveyor belt and it's accelerating, and it's actually reaching quite an impressive speed. It's about 50, maybe even 60 kilometers an hour. okay, on a legged machine. That's very interesting. Okay, so there should be some slow. So this failed right now at a certain speed, 28 miles per hour. Okay, and you can see that there is, you know, a leg pattern very similar to actual animals. Okay. Now, why I'm showing these to you? Because first of all, this is the cutting-edge research in the field. People are trying to build things like this, both in the university and in the industry. And another thing is, you can see that this thing is totally focused on the locomotion side. It's not focused on how you plan these motions. It's not focused on how you will perceive your environment. It's not focused on how this thing will be autonomous, in the sense that how it's going to decide what to do next, okay, in terms of its motion. A final video. This is a very recent robot that has been recently distributed to some of US universities, and a competition is organized by the Defense Agency of US. This is known as the Advanced, what was it called? DARPA Robotics Challenge. Universities are given one of these robots and they are being asked to perform certain tasks in a controlled environment. Okay? You can see that this thing is quite different from Honda's robot, because this is really, you know, this thing can implement all of the principles that you see on the previous robots in order to be able to balance itself and be able to react to its environment and so on. Okay? Any questions or comments at this point? So these are things that are exciting us to conduct research in legged robotics field in the sense that I'm describing to you here. Okay? Any comments or questions? Yes?
These robots do not have any sensors for keeping, right?
Well, they have some sensors. For example, they have definitely inertial sensors that are sensing what's happening in the body in order to give some feedback to the closed-loop controllers that are actually balancing the robot. So in that sense, they have, for example, our inner ear. Okay, as you know, we are being balanced by our organs in our inner ear, right? The cochlea, the so-called, where we can sense the gravitational vector, and even our eyes closed, we can actually maintain our balance. And you know that there are some sicknesses where your inner ear is affected by some bacteria. You no longer can maintain your balance. Even if you open your eyes, you cannot, you know, you feel like you are going to fall and you actually fall because everything, your sensors are twisted by the sickness. Okay? Any other questions? Okay. So what do we do? First of all, now I'm going to talk about a number of specific projects that we have conducted related with this legged robotics area. Our first project was actually based on building a six-legged robot that is inspired from an insect, okay, that is able to exhibit similar behavior to the quadrupeds and so on. It can run very fast. It can have an aerial phase. The legs are rotary legs like this. So there is an electric motor and a gearbox here. The leg is a C-shaped half-circular leg, and this thing is moving by the rotation of its legs. Okay, so there is a certain pattern being executed to move the robot. Okay, so when you do this very fast, the robot has an aerial phase. And it can have oscillations. It can oscillate from side to side. It can oscillate back and forth in a way that is similar to other legged animals. Okay? And it has been shown that the center of mass of the body actually exhibits a motion that is very similar to what is being exhibited by two-legged mammals like humans, as well as four-legged animals. Okay, so it bears interesting resemblances, and it's a robot that is very capable in the sense of being able to move in an uncontrolled terrain. Okay. Now, in this project, what we have done is we have built this robot. This is the PhD. This was based on the PhD research of my brother. Okay. Professor Sarandlı. We have built this thing, redesigned it with improved capabilities. This is the block diagram of the entire system. Essentially, there are two PCs embedded in the robot, and there are quasi-independent leg units. Each leg is able to control its motion, and there is a central pattern. The motion pattern is being distributed from the central computer to the individual legs. Okay. There are some, this strip is from our project final report, and I want to show you a couple of, or maybe one or two videos out of this, this report, okay? I'm gonna just randomly try something, okay? So this is the backyard of our department. So this was, this project concluded at 2010, so it's almost like 5 years old now, okay? But what this platform gives us, by designing this, we actually gained the capability to do a lot of research on this specific platform. Okay, so this is like a research platform. We don't want to take this to, you know, a disaster site and do something, but we want to work on scientific problems that can be tested on such a platform. Okay. Of particular importance for me is vision problems for legged robots. Okay, vision problems for legged robots suffer from particular problems, as I'm going to talk about in a minute. Okay, let me show you maybe one more video. Or okay, so these videos became part of our final report for TÜBİTAK. Okay. So this is the strip that is in the presentation, okay? This thing is actually quite capable in terms of being able to overcome different obstacles of different sizes, even things that are exceeding its leg clearance, okay? There was also, I believe, a stair climbing video that so this was also one of the tests that we had promised as part of this project. Okay, so even without any particular algorithm, just executing its regular gait, it is able to climb stairs. But if you do some specific motion design, specifically designed for climbing stairs, then you can do even better in terms of performance. Okay. Any questions or comments here? Yes.
Is it autonomous or remote control?
Well, in those tests, basically the device was not autonomous. It was being driven by the computer that is shown there. Okay, so there was an interface which was commanding the robot to execute certain motion patterns. But later on, we were able to generate autonomy in terms of having feedback from a camera, for example, so that it can actually follow certain targets or follow, let's say, a line on the ground and so on. Okay. Now, while doing this, designing the robot, we also started looking at certain modeling aspects. For example, modeling the kinematics of the robot is something interesting. You know, these legs, they have a certain way of interacting with the ground. You have to know how the leg-ground interaction is going to affect the attitude of the robot, because it has an immediate effect on the stability of the robot. And if you have dynamic behaviors, then not only the kinematics matter, but also the dynamic behavior of the robot is also becoming very important in order to design proper controllers for motion. Okay? At that point, it became interesting for us to know how these legs were behaving, because a particular property of this platform is that based on what is in the nature, the legs of this robot is very flexible. They are composite springs that when you run them very fast, they actually flex quite a lot. So when you're trying to model the dynamic behavior of the robot, you have to take into account how the legs will react as you impact the ground. Okay? So we started modeling both kinematically and dynamically the behavior of this robot. At the same time, we started also looking at how we can control hopping versions of this robot as well. Okay, that's a very feasible mathematical model. The single leg hopper is a feasible mathematical model to also understand how you will basically control these multi-legged robots. Okay. More recently, as is in the title of my presentation, we actually completed a project that was looking at sensory aspects of legged robots, in particular the vision sensor. Okay? So when we look at vision on a legged robot, it's somewhat different from, let's say, having a camera on a wheeled robot on a flat surface. Okay? The camera is actually exposed to quite a bit of vibrations and oscillations because of the leg-ground interaction. Okay? So what happens is that the visual sensor is actually acquiring video that is corrupted, in particular by what is called motion blur. Okay? Motion blur is what happens if you execute a very fast motion while the camera is acquiring its images. So individual frames are being corrupted because of the motion that is happening while the image is being captured. Okay? This actually shows, the frames show while the robot is walking, while its camera is looking at a particular target, okay, you can see that at different frames there is different amount of distortion in the video data that you are acquiring. Okay? You can see that at the right hand side here, the image is so corrupted that you cannot really do anything useful automatically on these images. And computer vision is based on acquiring images, processing these images in order to extract certain features out of it by automatic algorithms, so that you can detect objects, you can detect where you are, you can detect where you want to go, and so on. So everything suffers when your image quality is being degraded by the inherent motion of the platform. So as part of this project, we looked at different ways of correcting that distortion. Among other things, we designed a robotic head which is being driven by quite small actuators, so that this platform is able to move very fast, so that when you mount this on top of the robot and you acquire the motion of the robot, you can actually stabilize the top platform so that the camera is being exposed to much less motion, and so the images, the videos that you acquire are actually much better in terms of quality. As part of this project, because of my signal processing background, there was also a very interesting aspect of this project. It was based on the auditory sensor of the robot, so hearing. Okay, as you know, humans and other animals are using their ears in order to detect danger, in order to perceive what's happening in their environment, among other things. Okay? So what we tried to do in this project was, because our legged robot had this inherent property that legs are actually hitting the ground at a certain rate, and depending on the ground, you get a certain characteristic signature sound of this interaction. So we wanted to explore the sensory issues there, so that can we use the auditory perception in order to do something useful with this data. Okay, it turned out that by capturing the leg-ground interaction, you can very accurately detect what's the texture and material properties of the ground that you are walking on. Okay, we acquired something like 7 to 10 different surfaces, and we actually moved the robot at different speeds on these different surfaces, and just recorded the resulting leg-ground interaction sounds. And from these sounds, by using pattern recognition approaches, you can actually detect what surface you are moving on. Okay, that is important for us because the type of surface you are on has an impact on what kind of motion you have to execute with the legs in order to maintain energy efficient, fast and stable locomotion. Okay, if you have experienced, such a thing, if you, let's say, close your eyes and you are walking or running on a rigid surface, and let's say you suddenly transition into sand, you will immediately fall. Okay, the transition needs a change in the way you modulate your muscles in order to walk on a rigid surface versus walking on a, let's say, on a sandy surface. Okay, so if you run on, let's say, on concrete, and then you suddenly transition into a sandy surface, and if you don't have prior information, you will fail in your running behavior. Okay, so this surface was very important for us. So this was a way of being able to detect what surface we are walking on. Obviously, you can also try to help yourself with the vision sensor, because the vision sensor is also able to see, the surface which is ahead of you. So it might be an interesting way of research to combine, for example, visual perception and acoustic perception in order to get a more reliable estimation of what kind of surface you are working on. Okay. This is more related with my brother's research in the computer engineering department. This was a project, again a TÜBİTAK project, that was addressing the problem of how would you have artificial intelligence, in the sense that how would you make decisions on how to move your legs while you're also trying to maintain your balance. So it's a combination of computer science for decision making and control theory for maintaining balance. Okay, these two areas traditionally are very separate. Control people don't really too much bother about decision making, and decision making people are rather unaware of control theoretic contributions in this area. So he was using something called linear logic in order to integrate concepts of time, resources, the dynamics of the system into the decision-making problem. Traditional logic that we learn in computer science don't address dynamic systems. Traditional logic is about decision-making, and usually it's assumed that everything is static around you until you make a decision. You make a decision, you change something. Then you make another decision. Okay? In a system like this, you have seen, in a legged robot, everything is happening in a time-sensitive manner. Okay? Your decisions has to be aware of the dynamics of the system. Otherwise, your decision will come too late, or while violating certain constraints of the dynamic system. Okay? So that's also an interesting area of research. Now, so what's the future for us? Based on these numerous projects that we have done, now we want to go in certain directions. Obviously, there is a lot to do, but we can only work on particular aspects of research. Okay, you have to really select something and spend your time on. One interesting area that I'm interested right now is alternative approaches to stabilization of dexterous legged motion. That means, obviously, you can use your legs to stabilize yourself, But humans and other animals are also using other parts of the body in order to stabilize themselves. For example, we have our upper body, okay? Even if we don't move our legs, we can use the upper part of the body in order to maintain our balance, okay? We can use our arms. You have seen the Atlas robot, right? There was a simulated arm with weights on it. So it was using those weights in order to maintain balance, okay? For example, four-legged animals have tails. The tail is not a useless thing. If you carefully watch the cheetah, it's actively using its tail. The tail has a certain mass, and it can actually move this tail very fast in order to create a momentum that's going to help his body to move in a direction that it wants. Okay? So having a tail, also having other engineering systems for our robots might be interesting. For example, none of the animals have reaction wheels, but we know that our satellites are being positioned in space using reaction wheels. A reaction wheel is a mass, basically a wheel having a certain mass. In order to move your body, you apply a torque to the wheel accelerates, and because of action and reaction, your body has to move in the opposing direction. Okay? So you can have potentially you can have a reaction wheel within the body of the robot, so that by applying torque to the reaction wheel, you can try to stabilize your body, for example, so that your vision sensor is acquiring better images. Okay? So that's one area of research which is combining mechanical engineering and electrical engineering. Another area is basically we are not finished with this head concept. Okay? Animals are using their heads very effectively in order to maintain, let's say, an accurate sensory perception while the body is doing other motions. Okay? Animals do not attempt to stabilize their entire body, they attempt to stabilize their head rather than the entire body. Okay? So this head concept still has quite a bit of research to work on. I'm also interested in probabilistic algorithms for robotics. There is something called estimation theory that is related with how do I determine the state of my body. In order to do something about the way my body moves, first I need to be able to sense, the state of my body. So that requires that you integrate all of your noisy sensors, the vision sensor, the inertial sensors like we have in our inner ears, your touch sensors, any kind of sensors that you have, they have to be integrated into a consistent view of self. Okay? And that requires probability theory and estimation theory, the so-called estimation theory, in order to estimate the state of a dynamic system based on noisy sensor data and some models of its motion. Right? Finally, we still have a lot of challenges related with visual sensors on small outdoor ground robots. Visual challenges that are not initiated by the body of the robot, but challenges that are initiated by the surrounding environment. Okay? Think about this six-legged robot that is running in, let's say, our spring, spring weather and spring ground. Okay? There's a lot of grass. There's a lot of things around the robot. The visual sensor is buried inside this cluttered environment. Okay? Being able to sense something of interest, for example, a human walking far away, or let's say a path that you will follow within this cluttered environment is very interesting research. How do you filter, this noisy images so that you extract information that is critical for you? Okay? So we are also interested in processing image streams relating with our environment, as well as having issues related with, improving images due to our own body's motion. Okay? So these are things that we hope to spend time on in the near future. That's basically all I have for you, and I guess it's just about time. If you have any questions related with any part of the presentation, we can spend a couple of minutes on trying to answer them. Yes?
You talk about a robot which takes the sound from its environment. What type of sensors did you use?
This was a very simple stereo microphone that we mounted on the bottom of the robot. It was just acquiring, in a symmetric manner. It was mounted on the central axis of the robot, so it was acquiring, this contact sounds from the surrounding legs. And it was just a regular computer A to D card that was acquiring this sound data.
Did you specify some regions for different ground terrain texture, for example, some frequency range for the sound, some frequency range for the tough?
Well, we tried to do many things related with feature extraction. So after digitizing the audio signal, we basically subjected it to some kind of a frequency analysis. It's known as the short time Fourier transform. Basically, you move a window on the signal. For each window data, you perform a frequency analysis. You get basically energy in certain frequency bands, and then you reduce this data by saying that, okay, let me define, let's say, 10 bands, different bands of frequency. Let me sum all the energy in those bands, and that's going to give you a certain amount of features. Okay? Normally, the sound data is pretty intensive. You have lots of data, but when you perform this kind of frequency analysis, you can compress the data into some relevant, let's say, fewer amount of data that you can then use to make decisions.
By using this data, we can separate all different kind of...
Yes, we were able to separate up to, I believe, 8 surfaces with about 90% accuracy. Just plain analysis of the audio signal without any additional information. Any other questions? Yes?
I have two questions actually. Is it possible to use a gyroscope and eliminate the motion balloon?
Well, it's certainly one of the critical sensors that we are making use of, but it's not by itself sufficient to eliminate motion balloon. But it gives you information about what's the motion of the platform, and you can use this information to basically drive certain control algorithms that gonna, for example, move the head in a way that's gonna, let's say, if your body is moving like this, and you are able to move, your head in the opposing direction with a minimum amount of delay, then you can help reducing the motion.
Mechanically, using some sort of processing as approaches, is it not possible to use the data from gyroscope?
Well, as I said, the data from the gyroscope definitely has to be used in order to do something, but by itself, it's not something that's going to eliminate motion balloon. It's the sensor. Maybe one of the most useful sensors that you can use in order to apply certain algorithms to eliminate motion blur. Yes.
And how much important is the number of legs? When you increase the number of legs, is it possible to make something more stable?
Well, nature says that number of legs may not be critical, but obviously having a larger number of legs matters when you stop. Okay, when you stop, if you have 4 or more legs, you are statically stable. If you have 2 legs like humans do, and with a quite small area of contact, okay, if your algorithms shut down, you basically fall down. Okay, but dynamically, you can see that humans are very capable robots in that sense. They can move everywhere, they can run, they can jump. There are multiple things that we can do with our legs. And we don't need 4. We have evolved to not to use our hands for moving. We are not, running with our hands. But in the nature, obviously, 4-legged animals, insects are very powerful in their ability to move So we can see that maybe different sizes have different advantages. Maybe we don't completely understand that yet, but biomechanic people from biology are looking at issues with size, scale, weight, number of legs, and so on. But I don't know. Okay. Any other questions? Somebody else maybe? Yes?
Are these robots know their locations or they are just randomly born?
Well, this particular robot, well, you can put a GPS sensor on it if you're in the outdoors, and you can quite accurately get a feeling of your location. If you're indoors, you have to use some kind of either onboard or an external sensor. Okay? If you can use your onboard camera to look at, let's say, certain landmarks in order to determine your location. That's again a probabilistic estimation problem. Alternatively, if you're doing some experiments, for example, you can have external cameras tracking your robot so that you get a precise measurement of not only the location, but the entire attitude, you know, the angles of the body and so on. Okay? In our lab, we have a 6-camera system that is able to, if you put a tag on the robot, a certain number of reflectors, by using those cameras, you can very accurately measure the positioning and orientation of the robot in space, so that you can perform certain experiments. Okay? But ideally, we want obviously to be able to use the onboard sensors to get a feeling of our location. And that, as some of you might know, is subject of canonical probabilistic robotics algorithms like localization. Localization problem is about using your onboard sensors to have noisy measurements of what is around you in order to measure where you are. Okay?
Since that you are focusing on the indoor navigation, isn't it? Or
Well, we are not entirely focusing on the navigation problem yet, because we are looking at some other small problems that is surrounding it, let's say. In particular, for example, the vision problem was occupying my time for quite a while. So trying to correct the visual disturbances was more my focus rather than, you know, applying localization algorithms for this particular robot too. So we are working more on enabling technologies rather than the final application at this point. Okay, so if you have no other questions, well, thank you for listening to me.
Thank you very much for being with us.
Teşekkür ederim arkadaşlar. Dinlediğiniz için bu sıcak
Teşekkür ederim.
akşamüstü hepimizin enerjisi biraz düşüyor. Bende adrenalin var, sizde olmadığı için biraz daha yorucu olmuş olabilir. Hepinize başarılar diliyorum araştırmanızda. Görüşmek üzere.
Teşekkürler tekrar.